Welcome. This video covers simple linear regression in SAS. We've already looked at investigating a linear relationship using correlation and correlation analysis. Well, we can also investigate that linear relationship using simple linear regression. With simple linear regression, we do need to have a response variable that we might call y over here. And what we try to do is model that response variable as a linear function of one of our predictor variables. And so here, this is a linear function. Beta naught and beta 1 here would be our parameters of our model. And what we're trying to do is estimate those parameters from our data and then try to use those to either do predictions or to make inference about that linear relationship that we see. And so a picture here might help a little bit. So down here we have our x variable, our predictor variable on the x-axis, and we have our y variable on the y-axis. What we're assuming is that there's some true line, so this beta naught plus beta 1x is representing this true line that we see, but we don't actually observe our values right on that line because there's variability in our data. And what we need to assume to do our tests, or what we usually assume to do our tests, is that there's going to be deviations. If I observe a value of y at x1, I'm not always going to observe it right here at the mean of the distribution, but I might observe some values out here, some values out here, and very rarely I might get a value out towards the tail of that distribution. And what you end up getting is, if you had a whole bunch of points, we should end up seeing something that looks roughly like that, right? We have a scatter plot where our data follows roughly the same spread across the whole line, but it is observed in some sort of linear pattern. And so we boil all of our assumptions about this into this error part. So this is our error term. And what we do is we assume that those errors are IID normal, so they're independent, identically distributed from a normal distribution with the same variance. Again, all of that is going to be a little bit beyond us. Just know that we are going to have this underlying line that we're trying to estimate the parameters of, and we're going to try to use our data to estimate it. Then we're going to try to use our data to make statements or claims about that beta naught and that beta 1. So again, the overall question that we're trying to ask here is about the linear association between x and y. The slope here is actually going to determine the linear association. If that slope is 0, we would see no linear association between x and y. Basically, instead of doing a correlation analysis where we're trying to analyze R to make statements or claims about rho, we can use our sample slope that we're going to estimate from our data to make statements or claims about beta 1, our population slope. And again, if that slope is 0, we should see no linear relationship. If I have my x and y here and I have a line with slope 0, well, for any x, I'm really predicting the same y, right? Whether I'm x over here or I'm x over here, I'm getting the same prediction. So that is saying that there is no relationship, there's no linear relationship here between x and y. For a given x, I'm always predicting the same exact y. So essentially, we can boil our questions of interest down into questions about that slope term. So you might ask, if really all I'm doing here is understanding the linear relationship through either correlation or simple linear regression, why am I doing this more complicated version with simple linear regression? And the reason is that we are able to do prediction when we do simple linear regression, whereas we can't do that with correlation analysis. What this means is I can give my model a particular x, and I can estimate the value of y I should see, and I can also put error bounds on that estimate as well. How are we going to fit our models in SAS? Well, there is a specific procedure for doing regression analysis called procreg, but it requires you to do a few things that are manual, which aren't great. So we'll use procglm, which stands for General Linear Model, and allows us to do regression modeling and a bunch of other things as well. If you look at the help for procglm, you'll see a number of statements there. We're not going to utilize the class variable, so we're going to cross that one out. But the main options that we would use in procglm would, of course, be to specify our data set. We can change our significance level, alpha, and then we might request plots so that we can check our assumptions. The model statement itself is where we actually specify to SAS what model we're trying to fit. When we're doing a simple linear regression model, we just specify our y variable on the left, an equal sign, and our response variable on the right. Sorry, our predictor variable on the right. We can do then a slash and a number of useful options. So there is the CLPARM option, which gives us intervals for our population slope and intercept. There's CLM, which will give us intervals for future values, future mean. It will give us confidence intervals for the mean of y at a given x, and CLI, which will give us prediction intervals or confidence intervals for a future value of y at a particular x. And so we'll look at those in a little bit more detail later on. And as with most procs, you can do a by statement to break this up by a categorical variable. We are going to have to add in this extra quit statement at the end of our proc step to tell SAS that we're done modeling and to basically submit this code and start running it. Let's utilize that same exact data set that we were doing before with the correlation analysis. We had that all ORDS variable representing our response, and we might want to relate some of our numeric variables to that through a linear relationship. And so we'll focus on this unemployment variable. Here's how we would code that up. You can see that we're going to do plots equal all so that we get our plots that are going to help us understand our assumptions a little bit better. And then we're just specifying our y variable and our x variable. I'm then asking for both confidence intervals for our parameters and then confidence intervals for the mean response at our x values. The output over here on the right has a lot of stuff going on. We'll just briefly look through it. What we're doing here is a little bit beyond us, generally speaking, so we'll just talk about the general things that you would look at in these in this output. So this top part is called an ANOVA table, and this just gives us comparisons of variation. So these are all variations being measured from my data, and these are sort of standardized versions of these. And basically we use these variations to determine whether we have a significant linear relationship or not, and then this p-value over here that you see, this is going to allow us to test whether or not our model is useful. So if that p-value is very small, that means that we do have a significant linear relationship. So that's good. It seems like unemployment is useful for modeling the all ORDS. There's some other things that we commonly look at down in the next table. So R square gives us what we would refer to as a proportion of variation explained by the model. So here we would say that 62% of the variation in the all ORDS response variable is explained by the linear relationship with unemployment. So that's pretty good. We're able to explain 62% of the variation in our response. And then root MSE is going to be an estimate of how variable our population is. So that's useful to have too. And then what we care about, again, for looking at that linear association between all ORDS and unemployment, we would look at the slope row. So this is the row for our beta naught here. This is our row for our beta 1. And if we look over here, we get a p-value. This p-value, in this case, for simple linear regression, is going to be the exact same thing that you see up there. And then we also get a confidence interval for that slope. So we can see we have a very strong negative relationship here. Here's the output from the CLM option. The CLM option is going to produce confidence intervals for the mean response at every x value in your data set. Over here we have which observation we are corresponding to. So for every observation in our data set, we have a predicted value and then a confidence interval for the mean response for that x that is associated with that observation. Unfortunately, SAS does not tell you what the x values are. It would be great if they gave us what x was right here, but they don't. So you do have to relate this back to your overall data set. But you can see here that the observed y, so this is my y observed for this case, was about 5,600. My predicted was 7,000. So that means that my model was off by this residual here. It was off by about 1,448. And basically with this model, we can create confidence intervals for the mean response. So I went back and looked at the data set. The first observation had an unemployed value of 0.109. So for all observations that would have an unemployed value of 0.109, the confidence interval for the mean all ORDS value, i.e. the response, is between 6,800 and 7,366. So that's where we would reasonably expect the all ORDS value to be if we have an unemployment value of 0.109. Here is a graph that gives us that information sort of graphically, which is really nice. So remember that we had an unemployed of 0.109, so that's somewhere over here. And the estimate of it was, so the predicted was 7,083. So if we look here, 7,083, yeah, that's about right. Sorry, I'm off a little bit. So 7,083, about there. And then our confidence interval should be right about in that range. So again, that inner band is giving us a confidence interval for the mean response, so the mean all ORDS value at all x values that would take on an employee of whatever you're at. And then the prediction interval is for a future value of all ORDS for that x. We also got some plots from that plots equal all that are useful to check our assumptions. We haven't really talked too much about the assumptions, so we're just going to hand wave this a little bit, but what we want to see here in the top left is no real pattern and a roughly similar spread across there. We can see that there's a pretty strong pattern in the middle there, so this model might not be that great of a fit. We could probably do a little bit better. And then what we hope to see in these bottom two graphs we see here would be a straight line for that top or that middle left graph, and then a rough bell shape for that bottom one. We don't see too much deviation from that here, so this is checking on the normality assumption. We would say the normality assumption is probably okay. All right, let's jump into SAS and just do a quick simple linear regression example. Here we are in SAS. Let's go ahead and run a basic simple linear regression analysis on our wine data set. So I'll go proc GLM. We'll still use NCSU mywine. And I'll do plots equal all so we can see some diagnostic plots. And now we just need to specify our model statement. So we're going to model quality. That's our response here. And we can use any of our numeric variables as our predictor. I'll just use pH, just change it up here. We'll do /CI to get some confidence limits for future values. And then we'll hit run and quit, submit that code. This data set has a number of observations, so it does take a minute to run in this case. All right, we should check our log. Go to our log, it says, ODS graphics with more than 5,000 points have been suppressed. So if we do want to get our plots here, we need to add in this plots max points business. So let's go ahead and do that. Make sure that we can see our diagnostic plots. So it told us to do max points equal, I think you just do, I think there were 5,500, so let's just do 10,000 points. And then we still leave equal all to get all of those. So let's run that again. All right, so here's our output. Always check our log first. This time we didn't get any warnings and we don't have any errors, so that's good. If we look at our results, we can zoom in here. We do not have a significant p-value up here, so there's not a significant linear relationship. This p-value is not very small, right? We should see what we got or something worse about 11 or 12% of the time. That's not very rare. So whatever we do down here, it's probably not valid because we don't have a statistically significant result here. But that's okay. We can still see our estimated slope and intercept down here and p-values associated with those. This is a case where there are so many observations here, we're going to want to use our table of contents to get down to our plots. But first, we now have 95% confidence limits for individual predicted values. So this is not trying to capture the future quality of all wines with a certain pH, but of a future wine with a given pH. And then we can go down to our plots, which we should have in here. So if I scroll down, we've got our predictions, diagnostics panels. So yeah, we'll go down there to the diagnostics. And we can see here, we want to see a rough scattering here. That's good. Roughly straight line, that's pretty good there as well. So that's nice to see. We can look at our fit plot. That's another useful one. So notice that we did not have a significant linear relationship. This slope is really close to being flat and horizontal. And so that's why we're seeing that non-significant p-value. But you do see these dashed lines, just to sort of show you that again. The dashed lines here representing a confidence interval, what we call a prediction interval, but a confidence interval for a future value of quality for a given pH. The shaded line here is for the mean of all wines with a certain pH. And so that is a basic analysis that you could do in SAS. Great. So now we can investigate the linear relationship between two numeric variables pretty well. We can either use correlation or simple linear regression. Simple linear regression is a little bit better because it allows us to do this extra bit of prediction that we couldn't do before.